Good afternoon, everyone. My name is Ojas and I'm a senior at Frisco High School studying my ISM topic of RISC-V architecture. When people talk about processors, they usually talk about the clock speed or how many billions of instructions they can execute per second. But the performance is just not about the measurable metrics like the speed, it's also about efficiency, as it's the main thing which is affecting your clock rates or your instructions per second. And while a processor can run extremely fast, but if the instructions stall inside the pipeline due to the hazards or stalls, the performance will degrade and the efficiency will be lower. So instead of asking how, so instead of asking how like fast a processor is, I asked a different question: where is the performance lost inside the pipeline, and how can that loss be measured, and how that efficiency can be improved? And that shift changed everything. I moved away from describing the hazards towards quantifying them. And then that meant that I have to build controlled test cases, isolating the variables, and recording measurable metrics like the CPI and the total cycle count. And that was the moment of the project that moved from experimentation to the explanation. I understand why I chose RISC-V. To understand why I chose RISC-V, we need to first understand the instruction set architectures, or the ISAs. An ISA defines how software communicates with the hardware, and most processors use closed ISAs, like the x86 architecture and the ARM architecture. These are typically used by the big companies like Intel, AMD, Qualcomm, and Apple to make their chips, but those are proprietary and they can only be used by those companies to create those pipelines. But RISC-V is different as it's open source. So developers can try and improve the software so they can reduce the amount of stalls faced by the systems. And they're also used for teaching college students and high school students on how these RISC architectures work. And because it's open source, I could control the pipeline configuration and disable the forwarding and observe the hazards directly. And I was not limited to just treating this as like a text box or a sandbox, but I can also implement my own solutions into this. All of my experiments were controlled in rhymes. This is the five-stage RISC-V pipeline simulator, and this shows everything. This shows the instruction fetch, the execute, the memory, and the write back. And the interface shows instructions flow cycle by cycle. I could see when a register was written. I can observe a read after write hazard. I could watch a stall appear in real time. I can toggle the data forwarding on and off. Most importantly, I could measure uh, exactly where these stalls were. And one analogy I'm going to use to help you guys understand this is a traffic signal. So when there's not a signal light at a traffic intersection, cars don't know if they're meant to go or they're meant to stop. And this creates confusion as drivers will inch forward expecting some other driver to stop, but if they don't stop, then uh, the cars would have to stop and they would all have to stop. But here it's different. With data forwarding off, that's like not having a stop sign or not having a traffic light. So the instructions are not sure if they're meant to be able to go to the next stage or not until the entire cycle is complete and everything's coming back to the right memory. And this is really just where my original work and my final project differ, as my original work was talking more about how data forwarding was off, and my final product is more about how the data forwarding off works with the data forwarding on. And while data forwarding is on, it's like adding a traffic light to your intersection. So now cars know exactly when they can move, and instructions know when they can like go up to the next step. And this reduces the amount of stalls, and the CPI, the cycles per instruction, that's kept closer to one, which means it's getting more efficient. My research question was um, that whole thing. And once my mentor was established, I had my research question. How do data hazards impact cycles per instruction in a five-stage pipeline? More specifically, how does a measurable performance difference occur? And I tested the baseline execution, no operation-based stalling, and instruction reordering. And I focused more on the read after write hazards and the data forwarding on or off. My original work's design was that I designed a controlled assembly program that deliberately created these raw dependencies, and I disabled data forwarding in certain trials to simulate a constrained pipeline and make hard penalties more visible. I wrote those five assembly codes in microbench programs, and And program one was intentionally inefficient. It uses nested loops, repeated memory loads, and stores that explicit NOP instructions. This maximizes the memory traffic and hazard pressure. So this is like having lots of cars trying to go through an intersection which is not very well managed. But program two is still while it still used a double loop, but it reduced the waste by keeping intermediate values in registers instead of repeatedly accessing the memory. So the distance the instructions have to travel was reduced. The third, fourth, and fifth programs use single loop summation algorithm, while program 3 was clean ON baseline. Program 4 reordered instructions to reduce back-to-back raw dependencies, and program 5 unrolled the loop by a factor of 4 to reduce the branch overload. In the programs 3 to 5, it was basically like having the people in the cars carpool, so the amount of instructions would be lowered and it can be more efficient as more information can be processed in each instruction. In my data and results, my CPI results were for 1.71 for the baseline, 1.44 for the NOP, and 1.71 for the instructions reordering. But the CPI itself is not telling the entire story. On the right side of the slide, you can see these two additional graphs I made. In the first graph shows the instruction retired per program. As program structure becomes more efficient, the instruction retirement pattern changes significantly. And the second graph shows cycles per program. This is the most critical one because there's a dramatic reduction in the total cycle count between the inefficient versions and the optimized versions. And after collecting the data, I went into the analysis mode. One important realization I had was that CPI is not enough, and CPI can be interpreted alongside the total instruction count, the total cycle count, instruction count, and forwarding configuration. By instructing the reorganization of it, it mirrored what compares to automatically in the closed ISA systems. And by manually scheduling the instructions to reduce the raw dependencies, I was replicating the compared levels optimization closed ISAs typically do. Another insight was that predictable stalls can sometimes be preferable to uncontrolled hazards, as you would much rather have a organized traffic flow than an unorganized traffic flow. And this analysis forced me to think the architecturally rather than numeric. My first mentor interview, I spoke with my mentor Jeffy Chico, who is an embedded software engineer at ASML, which is a advanced semiconductor materials lithography company. And this company, like they manufacture the advanced semiconductor chips, like the machines to make them. They create those machines which they sell to Intel, to AMD, and to Apple. And he really emphasized that the processor architecture for fundamentals is essential in this industry. He also explained that tools like RIBES reflect the early stage micro-architectural validation concepts, while industry tools are more advanced, the reasoning process is the same. One key insight he shared was that with disabling forward and deliberately testing stall scenarios, it's not artificial. Engineers test this worst case condition to understand the performance limits. And this conversation framed my work, as it confirmed that measuring the hazards carefully reflected the real world engineering practice. My second mentor interview was with Vishnu Ghosh at Texas A&M University. He is a senior software engineer in the Research Information Systems division. And what we really talked more about was that it's not just about the results which I'm trying to go after, it's about the documentation, the reproducibility of these results. And he encouraged me to define how I was using the processor configuration, what forwarding settings I was using, instructing sequences and the programs, and the cycle counts and the CPI calculation. And he also told me that I should try and present my work in an IEEE format. So in college, if I decide to like revisit this topic, it will be easier to publish a research paper for this. And before my mentorship, my work was essentially like a simulation demonstration. And after my mentorship, it became more of a controlled architecture performance study. And there's several key changes I made was I defined the processor configuration explicitly, documented the forwarding assumptions, structured the data tables, and adopted the IEEE outline. And this comes directly from the mentor's feedback. This is my original works research board, and this shows my original work and everything which led up to it. And over time, I made sure to include the measured CPI comparisons I made, the cycle count graphs, the pipeline configuration notes, and the industry relevance this has. And this project is not finished. My next steps include expanding the hazard chain depth, modeling the range prediction models, and extending the analysis to the cache behavior using FPGA minions, and, and combining the study into an IEEE paper. Thank you.
Any questions? You guys all ready to write your own computer programs?